Hi, welcome to the second video in my Proof by Induction Differentiation series. In this video, we're going to have a look at proving the following derivative, or should I say nth derivative. Now, I actually haven't done this problem. What I want to do is I want to prove my point of that algorithm I talked about. So where we're going to do the assumption, and then the consideration, and our whole idea is to use that trick that we saw before. The derivative of the nth derivative is the n plus 1th derivative. We're then going to write down our target and we're going to try focus to try get this formula, but for k plus 1 or whatever we're doing. So let's have a go, let's see how this goes. So first of all, let's do the base case. So base case, n equals 1. So we've got the first derivative of etx cos x. Well, by product rule, this is derivative of etx, which is etx, multiplied by the other function, plus the derivative of the other function, which is minus sine x, multiplied by the function that we didn't differentiate. Pulling out a factor of etx is the same as etx cos x minus sine x. Now, if you're not familiar with Rcos form, it would help to be familiar with it because that's where this formula has come from. First of all, we know that R is equal to the square root of the coefficients. So we have 1 squared plus minus 1 squared, which is the square root of 2. And now if we were to expand this, we would have root 2 cos x cos alpha minus root 2 sine x sine alpha. So if we want the coefficients to be the same, if we want this to be identical to this, we need to have the same number of sine x's and the same number of cos x's. So in other words, I need to have root 2 cos alphas. I need to have root 2 sine alphas, or minus root 2 sine alphas. Now from the first equation, we see that we only have 1 cos x, and we only have minus 1 sine x's. This gets you that cos alpha equals square root of 2 over 2, and sine alpha also equals square root of 2 over 2. And well, both of these have the same angle as the solution, and that's pi on 4. So we're done. We're done with this example. So yeah, quite a tricky base case, but what you'll see is if you put n equals 1 in, you're going to get exactly this formula. Because now if I put the red back in, we've got etx times root 2 cos x plus pi on 4, which is exactly what we had for that formula at the top. All right, next let's consider our assumption. So let's assume that this formula is true for n equals k, i.e., so we have the kth derivative of cos x etx, that's right, yeah, we'll go the other way around, is equal to 2 to the half k etx cos x plus k pi on 4. So next, what we want to do is we want to involve our assumption. So I'm going to do consider n equals k plus 1. So we're going to do the derivative of the kth derivative, and that's our k plus 1th derivative. But well, according to our assumption, we're doing the derivative of this bad boy. So 2 to the half k etx cos of x plus k pi on 4. So we can bring that 2 to the half k out to the front. We've then got derivative of etx multiplied by the other function. And then we're going to have derivative of this function multiplied by etx. So it's minus sine of x plus k pi on 4 etx. Like so. So pulling out the etx, we're going to get 2 to the half k etx cos of x plus k pi on 4 minus sine of x plus k pi on 4. Okay, now what we're going to do is we're going to write out our target. Our target is to convert this into the form where we have 2 to the half k plus 1 etx, so the etx is in the right form, and then we're going to be multiplying by cos x plus k plus 1 pi on 4. So we've got to somehow get this cos x plus k plus 1 pi on 4, and we need an extra square root of 2 at the front. Now, what I kind of realize here is I spot something very similar to what we had in our base case. So if I just scroll up to our base case, we've got something kind of similar to the base case, except we haven't got x now. We've got x plus k pi on 4. So what I'm going to do is I'm going to say that theta is equal to x plus k pi on 4. So this is going to convert this to 2 to the half k etx cos theta minus sine theta. Now we saw actually that we've basically done this. We've already converted this into just a cos. So this is the same as 2 to the half k etx times the square root of 2 cos theta plus pi on 4. Like so. All that's left to do, we can bring out the square root of 2. That will give us 2 to the half k times 2 to the half e to the x multiplied by, now replacing cos theta with the x, we get x plus k pi on 4 plus pi on 4. And well, this is indeed our target. So we get 2 to the half times k plus 1 e to the x cos of x plus k plus 1 pi over 4. And well, at this stage, we can now do our conclusion. So, as true for k plus 1 when true for k, and true for base case n equals 1, by mathematical induction, it must be true for all k greater than or equal to 1. And we're finished. Quite a hard example. We're going to have a look at another example later on, but thanks for watching.